Hi everyone, we'll start in about a minute or two. Alright, good afternoon everyone, and today's lecture is going to be on the start of the Fourier series, which plays a very important part in signal analysis, especially when you're trying to observe the frequency components of the signal in particular. This technique for the Fourier series also transfers towards your communication course next semester, as well as some aspects of it will also transfer towards your control systems and your power analysis courses as of such. So if we watch a general signal sinusoid form here, we can basically see that if we try to characterize it, we tend to have some signal amplitude and we'll tend to have some periodic time of the signal itself. And this will be respect to amplitude versus time accordingly. And in asking what's the frequency of the signal, basically we can analyze it such that we can say, okay, at this point is at t equals 0, and then the next peak occurs at like t equals 6 point something, and we say 1 divided by the 6 point something will give us the frequency of our signal. So this is what the signal looks like when we have it with respect to time. But we can also represent the signal in terms of signal frequency versus amplitude. Basically, when we draw this, the y-axis here will be the amplitude, and the x-axis here will represent the frequency. And the reason why we can get away with this representation of signal frequency versus amplitude is because we know that the signal from before was sinusoid in nature, and as of such, we can represent it using a very simplified form here because of that nature of the signal. So if we have cos 3 omega t, where omega was the frequency of the original signal, and we can see basically the signal just speeds up by about 3 times because of this multiplicative factor. When we transfer this to a signal amplitude versus frequency graph, it basically means that we have the same amplitude, but the frequency here just multiplies by 3 accordingly, and we just shift the frequency from 0.15 Hz, which was the original frequency, to 0.45 Hz because of this multiplicative factor here being 3f. So that what happens when we have the same signal but just multiplying the frequency altogether. It just shifts the signal amplitude representation to the left or right in that graph. What happens when we add two cosine signals with different frequencies? So let's say the first one here was cos omega t, and the next one is cos 3 omega t. And the time domain, when we add these two signals, we get like a mixture of representations here, because they basically add and subtract amplitudes accordingly depending on the instantaneous value in time. But when we represent this signal here in that signal amplitude versus frequency graph, it basically is just going to be two lines here, representing the individual frequency components when we added them together. Because both signals individually have the same amplitude, but all that's different about them is just the frequencies altogether. So when we actually do the amplitude versus frequency graph here, we just draw the individual frequency components of each one of these signals. If for some instance, let's say the cos 3 omega t graph had a different amplitude, let's say it was like 0.8 or something, this arrow will just drop down to represent this change in amplitude here for 0.8 as of such. So basically, once we keep on adding sinusoids of varying amplitudes and multiples of the original signal frequency, we just keep on getting like a whole set of different things, but we can then see that the graphs itself, once we pay attention to being multiples of the original signal frequency and varying amplitudes accordingly, is that we tend to approach something looking approximately like some sort of square wave. That brings us to our Fourier series and our Fourier transform. But for this week, we're only going to be talking about the Fourier series. Next week, we'll be talking about the Fourier transform. So the guy who invented it was Jean-Baptiste Baron de Fourier, and he basically presented a paper that could say any periodic signal can be represented as a sign of sines and cosines. But at the time when he theorized it, no one was able to prove it until like a couple years down the line. Someone actually sat down and did the math to prove it, and because he made the theory, they named the proof and the theory after him. Actually, he's also credited for the discovery of the atmospheric greenhouse effect. So basically, what the Fourier series say is that for any continuous time signal x of t that is represented with a period t, and once that period t can be represented as 2 pi divided by omega naught, where omega naught is the natural frequency, the Fourier series representation of that x of t signal is given by a naught plus the summation between k equal 1 to infinity of ak cosine k omega naught t plus bk sine k omega naught t as of such. Now the equation looks a little bit scary, and it's not going to be very scary at all, because the only components that you're going to have to solve for will be the a naught component, the ak component, and the bk component. And the only time when you'll be solving for these three components is when we actually are required to use the trigonometric representation of the Fourier series, which is this given equation on top here. So once we are using the trigonometric representation and they ask you to solve for the Fourier coefficients, that means you'll be solving for a naught, ak, and bk accordingly. Those will be the only three coefficients you'll be solving for once you're using this trigonometric representation. And we'll be focusing on the trigonometric representation in tomorrow's lecture and how we actually solve for those coefficients. But in today's lecture, we're going to be looking at a different form of the Fourier series, which we will be approaching to in a couple of slides. And just to expand on this a little bit, the trigonometric representation basically shows that the a naught coefficient here remains constant, but a1, a2, and a3, and b1, b2, and b3 are basically coefficients representing the multiples of the omega naught frequency. So a1 will be represented with omega naught by itself, but a2 will be 2 omega naught, a3 will be 3 omega naught, same thing for b1, b2, and b3. There'll be omega naught, 2 omega naught, and 3 omega naughts accordingly. So the a naught coefficient is what we refer to our DC average or zero frequency value. And this actually is going to play a very important point in this lecture as well as tomorrow's lecture as to why the DC average or zero frequency value is required and is independent of the A1, A2, A3, and B1, B2, B3 values accordingly. And basically, because we say it's from A1 to AK and B1 to BK, AK and BK here basically the amplitudes of the respective cosines and sines, and they're basically weighted amplitudes accordingly for each one of those multiple of frequencies. And the reason why we call it the multiple of frequencies is that we also refer to these as harmonics. harmonics in particular, basically the same thing. It's just a multiple of the original signal frequency. So A naught A is our DC value, but at A1, which is 1 omega naught, we refer to this as the fundamental frequency. And then when we go to 2 omega naught, we say this is the second harmonic, 3 omega naught will be the third harmonic, 4th harmonic will be 4 omega naught, and so forth, until the kth harmonic, and so forth if you're required to sum up to that point. So in the spectrum, each sine and cosine term will basically represent a single frequency because they're going to be at omega naught. And then that will be at the fundamental frequency, and then for like the first harmonic, well, the fundamental frequency is the first harmonic. When you hit the second harmonic, it's going to be another single frequency, the third harmonic, another single frequency, and so forth. And the collection of those frequency components is what we refer to as the spectrum of the signal. So basically, the same signal amplitude versus frequency graph you've been seeing is actually what we refer to as the spectrum of any summation of sine and cosines accordingly their weights and amplitudes. And in particular, if you're using the Euler relationship for cosine x and sine of x, we can compact the Fourier series into a very neat form here, which basically gives us the shorthand version of the Fourier series. And we refer to this as the analysis equation of the Fourier series. Now, it's kind of important that you remember and make an index of this with respect to the Euler's relationship for cosine x and sine of x, because these relationships tend to help you shortcut your work quite a lot. And it may not be evident in this course, but when you reach your courses next semester, these Euler relationships will help you a lot with the mathematics involved in those courses. So this CK equation here, which we refer to as x of t with the summation series of ck, e, j, k, omega naught t, is what we refer to as the complex exponential or analysis form of the Fourier series. And the summation series, as we just now saw here, went from k equals to negative infinity to k equals to k up to positive infinity. And this just basically, in mathematics, you think, okay, maybe this implies negative frequencies, but no, it doesn't imply this. It's because the coefficients themselves gives us like a mathematical artifact of complex numbers. So basically, when you're solving for those coefficients, you will end up with complex numbers accordingly, in some cases, instead of just real values. And that's the only reason for k going from negative infinity to positive infinity. When you actually apply the equation, you will not be bothering with the negative coefficients as of such. You'll be starting from k equals 0 and going towards positive infinity, or to some set value of k is required in the questions. So if we watch the trigonometric series here and the complex exponential series here, basically represent the same Fourier series equations. AK here is represented by ck plus c of negative k, and bk here, represented in our sine terms, is represented by j of ck minus c to the minus k here accordingly. So our AK cosine terms will basically be real terms here with respect to ck and c to the negative k. But our bk sine terms here will have an imaginary value with respect to this j value here at the start of the equation. And that's basically shows how the AK and the bk values are related to ck here, mapping the trigonometric form to the complex exponential form. But for today's lecture, we're going to be focusing on the complex exponential form, and how it actually can help us with solving for particular characteristics of the signal with respect to its harmonics and its amplitudes. So, as we saw before with respect to our trigonometric form, when we are at 0 with respect to the index, with the index being k, this will actually give us our DC component, or average or zero value component. But when k goes 1 and 2 and 3 as of such, it will represent our first harmonic, our second harmonic, and our third harmonic accordingly. Just remember that the first harmonic is also referred to as our fundamental frequency. So basically we had our complex exponential form here, but we also need an equation here to solve for C of k, which is basically going to be our amplitudes for each one of those harmonics. The CK equation is given by this equation here, which is 1 on t integral of t on 2 to minus t on 2 of x of t e to the minus jk omega naught t dt. And this CK equation here is very similar to the Laplace transform manual integral equation as of such. So in particular, it's important to remember this CK equation because it actually, most of the questions that you end up getting that asks for the amplitudes of harmonics will actually rely on the CK equation in particular. So basically, our complex exponential form, our analysis equation, basically will tell us what frequencies are present because we'll be watching this with respect to omega naught and its multiples. But the synthesis equation being solving for CK here, basically will tell us the amplitude or magnitudes of those frequencies in particular. So that's why this CK equation here is more important than the analysis equation here as of such. Because the amplitudes at those frequencies typically is what is asked of in questions in particular. Once it's basically say they want to know what the amplitudes are at probably like the first 3 harmonics and so forth, you'll be using the CK equation as of such. And you won't really be using the analysis equation to actually get this, because CK here represents the amplitudes at those frequencies. So for any given continuous time period signal, that Fourier series equation can basically tell us the harmonics which makes it up, the amplitudes at the harmonics given by the CK values, and the frequencies by the k omega naught values as of such. And these 3 characteristics here basically give us the spectrum of the entire signal. So let's actually look at how can we apply the CK equation into a physical example. So we have an example graph here, which is basically a square wave with a set period, and this we have a set amplitude here of 1 for when the square wave is on and 0 for when the square wave is off. And we also have an imposed time here for when it's on being t1, and we also have some set times here on the x-axis being t on 2 as of such. And we're going to see how this t1 and t on 2 is going to relate to each other for us in solving for our CK values in particular. So the question here asks for the DC level of this signal, and that means basically that we want to be solving for C of naught. So the frequency of the DC component will be at 0 Hz because it's DC, there's no frequency involved with it. So this will be at k equals 0. If we watch our CK equation and we put in k equals 0, the CK equation will result to C naught being equal to 1 on t in between t1 here and negative t1 of x of t dt, where we integrate it as such. And we get C naught here equal to 2t1 on t if we do this integral in particular. So I'll actually do the work for the integral here to show that it's actually gives us that. So in between t1 and negative t1, x of t is going to be 1. So when we actually resolve this, we'll get 1 on t multiplied by 1 into t1 and minus t. Basically, when we go about doing this, we get 1 on t into t1 minus t1, and that basically will give us this value here, the C naught. The question can be expanded such that, let's say, if the signal had a 50% duty cycle square wave, what will actually be the DC level? Basically, we need to establish a relationship between the on time of the actual wave that is given to us here and mapping this to the duty cycle that which is asked of us to get to the DC level. So the on time of this wave here, which is given to us, is basically, we can see it's T1 here because it's 0 to negative T1, and also T1 here because it's 0 to positive T1. So this is going to be 2T1 for which our actual waveform here is going to be on for. And for a 50% duty cycle, that's basically going to be T divided by 2, where T is actually representing the time of that duty cycle. And we know that C0 here was 2T1 on T. So we have 2T1 here, and if we substitute this accordingly into our equation, we basically get T on 2 divided by T, and the T's basically cancel, so we end up getting C0 is equal to a half. Let's say, for instance, that instead of 50% duty cycle, let's say we had to solve for 25%. So what that means, if it's 25% duty cycle, is that it's going to be 2T1 mapping our on time of our wave is equal to T on 4 instead. And then, because we know C0 was 2T1 on T, when we solve for C0, this will now be T on 4 divided by T. If we rectify this, it'll be T on 4 multiplied by 1 on T, and the T's here will cancel, so we end up with a value of quarter. So basically, once you have a question asking you what's going to be the DC level and they give you a respective duty cycle, you need to make sure that you satisfy this condition here first, which is going to be that the on time for the existing waveform that you have here is going to be equal to that of the duty cycle in terms of T. As we saw here, for a 25% duty cycle, the on time of the wave here is going to be 2T1, but if it's 25%, that's going to be T divided by 4 accordingly to give us this 25%. And we already solved for C0 here in terms of T1 and T, so we just say, okay, we have 2T1 here, substitute that equivalent to T on 4, and we just do our mathematics accordingly, and we get C0 here is equal to a quarter for a 25% duty cycle. For our 50% duty cycle, we did the same method as of such, but instead it's going to be T on 2 representing this 50% duty cycle. And when we substitute in 2T1 equal to this, we end up getting C0 equal to a half. Alright, so before I move on to the next example, are there any questions regarding the solution for the DC level of our signal here? Alright, doesn't seem like we have any questions, so we'll be moving on to our second example here as of such. So our second example basically asks us what's going to be the amplitudes of the first three harmonics of the same signal that we had from before. And this is actually where we start applying the CK equation again, but in this time, instead of k equal being 0, we'll be going for k equal 1 to 3 because of the first three harmonics. So we'll go back to the CK equation here, and if we apply it to our particular case with the exponential form here as of such, if we integrate this equation with respect to the exponential form, for any general square wave which has a set period, the CK equation here will resolve into sine 2 pi k t1 divided by t, all divided by k pi as of such. I want to make a note of this in particular because I want to check back the CK equation. Because I think something's a little bit off with the mathematics here. But for now, we'll be using this equation. If there's something off about it, I will fix it and I will rectify it in the slides and I'll let you guys know. But for our illustration purposes, we'll be using the CK equation here as of such. So basically, once we do the integration here with respect to the exponent form, we'll end up getting the CK equation here equal to sine 2 pi k t1 divided by t, all divided by k pi. Oh, okay, we have a question here. Sure, I can go back how we got the 2t1. So, the 2t1 part represents our on time here of our signal. So, between negative t1 and 0 here, if we just take the magnitude, this is just going to be t1. And then between 0 and positive t1, if we just take the magnitude here for this time, it's also going to be t1. If we add those two magnitudes together, we'll end up getting 2t1 for only when the signal is on here represented. Alright, so after we resolve our integral form here for CK, we get our form here. I still need to make sure I verify this equation in particular for this integral. But we'll be using this equation for now. If something's wrong with it, I'll let you guys know. I'll fix it on the slides accordingly. For our 50% duty cycle wave, we basically saw that for our on time of our wave, which was basically to T1, was basically mapped to a 50% duty cycle being just T divided by 2. And if we solve for T, we get T is equal to 4 T1. If we substitute T here being equal to 4 T1 into our CK equation here, what will happen is that our CK equation will now become sine of 2 pi k into T1 divided by 4t all on k pi. And then this here will end up being sine, and we work out all the cancellations here in the brackets. We're going to get a half, the t1s will cancel, pi k on 2 divided by k pi. And in solving for harmonics, we basically just substitute k here being 1, 2, and 3 on our numerator and our denominators as such. And we'll get c1 here equal to 1 divided by pi, c2 will be 0, and c3 will be negative 1 divided by 3 pi. And we basically see, like, if we end up solving for c4, we'll get c4 equals 0, and then c6 being 0, and c8 being 0. And basically that means for all even indexes, we'll end up with a value of 0. But for all odd indexes, we'll end up with some value with respect to 1 divided by pi as of such. The terminology for this, when this effect happens, is that we refer to this being that the signal itself only has odd harmonics, because for every odd index, we'll have a non-zero value, and for every even index, we'll have a 0 value. If it was such that it was the opposite, where for, let's say, C1, C3, and C5 would have been 0, but C2, C4, and C6 as of such would have had some non-zero value, in that case, we will refer to that being such that the signal has even harmonics. Because for all even indexes of k, we have a non-zero value for ck. So if we plot the spectrum of this in particular, we have our DC value, which basically resolves to 1 divided by 2. And then we have at our first harmonic or fundamental frequency, we have an amplitude of 1 divided by pi here. And then for a second harmonic, it was 0. And then for a third harmonic, it was negative 1 divided by 3 pi, like only as of such. Alright. Yeah, I'll go back through this one more time. That way you guys can understand what went on here. So for this second example, we were asked about finding the amplitudes of the first 3 harmonics, including the fundamental of the signal. So that would be when k is equal to 1, 2, and 3 for our ck equation. Right. So when we integrate x of t here between t on 2 and negative t on 2, with respect to the exponent form here, e minus jk omega naught t dt, the resultant integration will give us the ck equation resulting in sine 2 pi k t1 divided by t all divided by k pi. And like I said, I want to make sure I verify this equation before we say, okay, this is actually the actual equation for this. So I will check back the math for this and make sure this equation is correct. But for illustration purposes right now, we'll be using the ck equation. So we have t1 and t here in our brackets. And we need to get a mapping for t and t1. So for 50% duty cycle, which is basically going to be t divided by 2, this needs to map to the on time only for our graph. So let's go back to our graph that was given here. And basically, when we have a non-zero value, or basically representing our on time for our graph, this basically is going to be between negative t1 and positive t1. And the time in between negative t1 and 0, if you just take the magnitude, it's just going to be t1 here. And the time for the next part of it was going to be between 0 and t1, so the magnitude of that is t1. So if you just add the 2 magnitudes here, you'll get 2t1 accordingly. So 2t1 representing when the signal is on here in our graph, being when this is a value of anything other than 0, is going to map to our 50% duty cycle, which is going to be t divided by 2. And then if we map this accordingly and make t the subject of the formula, we'll get t equal to 4t1. So because we now know that t is equal to 4t1 here, we're going to substitute this into our ck equation as of such. So if we say t here is equal to 4t1, and we substitute it in, we'll get sine equal, this will be equal to sine into 2 pi k t1 divided by 4t1 here, because we substitute t here is equal to 4t1, all divided by k pi. The t1s cancel. 2 and 4 here will give us a resultant value of 2 on the denominator here. So this entire value here in the brackets will end up being sine of pi k divided by 2, all divided by k pi. And when it's time to actually solve for the values of those harmonics, be our amplitudes, that basically means that we'll substitute k equal to 1, k equals 2, and k equals 3 as of such. So I'm going to go to the next slide and I'll show you how this is. So we have our ck equation here is equal to sine of pi k on 2 divided by pi k. And let's say we wanted to solve for c1. So k is equal to 1. c1 is going to be sine of pi on 2 divided by pi. Pi on 2, when you check that back in angles, it's going to be 90 degrees, and sine of 90 degrees is going to be 1. So this will resolve to 1 divided by pi. C2, where we say k is equal to 2, that means we'll end up getting sine of pi, and sine of 180 degrees, because pi is 180 degrees, is just going to be 0. So that's how we end up getting k equals 2, because if 2 is here, these 2's will cancel, so we get sine of pi on the numerator, and sine of pi is basically 0. So this entire thing here will resolve to 0 for when k is equal to 2, so c2 goes to 0. And then for c3, this will be 3 pi on 2 here on the brackets, and that's basically sine of 270 degrees, which will be negative 1 on the numerator. And k here was 3, so that's 3 pi on the denominator, so that's how we get minus 1 on 3 pi as of such. So the key here is that in solving for these amplitudes for each one of these harmonics, where k is going to be our first harmonic or fundamental frequency, k equals 1 will be our first harmonic or fundamental frequency, k equal 2 will be our second harmonic, and k equal 3 being our third harmonic. It relies on us solving the ck equation integral form here for our actual graph. And like I said, for this particular square wave, when you do the resultant integration here, we end up with ck equals to this form in particular, sine of 2 pi k t1 on t divided by k pi. The next step will be to make sure that you establish a relationship between t1 and t, and this is actually given in the question to you. So in the question, they basically told you that we have a 50% duty cycle. And in mapping the duty cycle to our actual waveform time here, this is going to be mapped to the on time of the wave. Now the on time of the wave will be for when the wave does not have a 0 value. So for this particular case, where the wave doesn't have a 0 value, is in between negative t1 and positive t1. If we take the magnitude here in between these two times, it will just give us 2t1 accordingly. So we say that 2t1 is going to be mapped to 50% duty cycle, which is going to be t divided by 2. And we make t the subject of the formula, so we get t equals to 4t1. And once we have t is equal to 4t1, we substitute this into our ck equation here as of such. Because the objective here is just to try and get rid of this t1 component and the t component altogether. So in getting rid of it, we say t here is equal to 4t1, the t1s cancel, and we have 2 pi k on 4, which basically is going to resolve to pi k on 2. Our denominator basically remains the same because it's just k pi. And once we have this form here equal to ck, which was ck equal to sine pi k on 2 divided by pi k, We just substitute k equal to 1, 2, and 3 accordingly, and we solve for each one of those. So C1 will resolve into 1 on pi, which was given by our work in here. C2, we basically saw that it will be 2 pi divided by 2, which will be sine of pi was 0. So C2 will resolve in 0. And C3, we basically saw it will be sine of 3 pi on 2, which will give us a value of -1. And on the denominator, it will be 3 pi. So we end up getting -1 divided by 3 pi accordingly for C3. So once you have that CK equation and you get rid of the T1 and the T components, then you can just go ahead and proceed with substituting K equals to whatever values you require for solving for the amplitudes for those particular harmonics. And in this particular case, we saw that for all odd values of K, we had non-zero values. But for all even values of K, we had 0 values. So for this particular signal, we say that the signal only has odd harmonics. If it was the other way around, where for even values of K we had non-zero values, and for odd values of K we had 0 values, in that particular case we say that the signal will have even harmonics. Alright, so are there any more further questions regarding this particular example? So this value here isn't referred to as a harmonic at 0. This is referred to as our DC value. If you have to say that it is a harmonic, you can basically say this is the 0th harmonic. But basically it's just the DC value. There's no frequency assigned to this particular value. Alright, so for your homework, basically you're going to have to require to find the values of the first 3 harmonics, including the fundamental frequency, being k equal 1, for this particular signal as of such. And assume that this signal also has a 50% duty cycle when you're working with this. So try this out for your homework and see what values you get for C1, C2, and C3. You can also try to solve for the DC value, but the DC value in this particular case will also resolve 1/2. So it wouldn't be CK is equal to 1/2, it will be C0 is equal to 1/2 in this particular case. But C1, C2, and C3 will have different values altogether. So C0 here was basically going back to our CK equation. So let's go backtrack a little bit to get our CK equation. So hold on, I'm going to do this from scratch for you to understand why it's this. So we'll have our CK equation here being 1 on t integral between t on 2, negative t on 2, and x of t e to the minus jk omega naught t, right? And which basically say we're going to be solving for when k is equal to 0. So when we substitute k is equal to 0 into this equation here, we get this e here going to the power of 0. So e to the 0 is basically 1. So now we have our CK equation here being C0 is equal to 1 on t integral between t on 2 and negative t on 2 of x of t only. So if we apply this accordingly to our question, we have c of 0 being 1 on t here. And in this particular case, our periodic time here is going to be in between t and 0. Of x of t, and when we resolve this out accordingly, we get C0 is equal to 1 on t in between 2t1 and 0 of 1 dt. So I'm going to make some space here because I need space on the slide to solve this for you. So this will go such that it will be C0 1 on t, and this will be t here in between 2t1 and 0. So T0 here will end up being equal to just 2t1 on t. So I told you guys earlier to assume 50% duty cycle. Now, in assuming 50% duty cycle, that means we can establish a relationship between T1 and T accordingly. So we basically see here that the on time for our graph here, between 0 and t, is just going to be in between 0 and 2t1. So our on time here basically will be meaning that when the graph has a non-zero value. So the time for when the graph has a non-zero value is in between 0 and 2t1. So that's going to be just 2t1. And then if we say 50% duty cycle, this basically means that for our entire periodic time, it's going to be 50% of that. That's going to be t divided by 2. Rearrange this. We got t here is equal to 4t1. And then substitute into C0. T0 will be 2t1 divided by 4t1. So basically give you a half. So in order to get that C0 value, even after you do your integral here, remember your integral here will be in terms of t1 and t. But you also need this duty cycle here in order to get a mapping in between capital T here and T1 accordingly. And to get this mapping, we basically say that the on time here, or basically when the graph that is given to us has a non-zero value, we need to know for what time does that exist for. So we basically see that when the graph here is not at 0, the time that it occurs is in between 0 and 2t1. So this on time here is going to be 2t1 mapping to a 50% duty cycle. And the 50% duty cycle, when you map this with respect to t, it's just going to be t divided by 2. So this comes like it was just 50t divided by 100, so that resolves into t divided by 2 because of that 50%. And then if you make t the subject of the formula here, you get t equals to 4t1 when you just carry across this 2 here onto the left hand side. And then you substitute that accordingly into your C0 equation here. So you put t here is equal to 4t1, and the t1's cancel. And you get 2 divided by 4, which will just resolve to 1/2. So the homework basically is just use the CK equation that we had from before and resolve that in terms back to our sine of the bracket value divided by k pi. And then just substitute in the same 50% duty cycle here that we saw to get rid of that t1 component accordingly in the brackets. And then you just substitute in your values for k equal 1, 2, and 3 as of such. Thankfully, you guys actually have auto integrators which can actually simplify the integration process for you online. If not, it's fairly simple to actually find out what is going to be the integration of a square wave. And you can actually get that. But like I said, I need to verify the map for that CK equation that we saw here. I need to verify the map for this CK equation to make sure that it resolves to this equation as of such from this resultant integral. And if it's a different thing, I will change it accordingly on the slides and I'll let you guys know what's the correct equation. But that would be the method for actually solving for how you get the first 3 harmonics. Basically being the same method that you did for example 2. Alright, so that brings us to the end of today's lecture, and in particular what we saw is how do we apply the analysis equation or the complex exponential equation to finding the amplitudes of the amplitudes at certain harmonics within our x of t signal using the Fourier series form. And the only time when you'll end up using this CK equation in particular is when the question specifically asks for the values or the amplitudes of the first how many harmonics. That's the only time you'll use the CK equation. In tomorrow's lecture in particular, we're going to be focusing on the trigonometric form of the Fourier series and how do we solve for the A0, AK, and BK coefficients in particular. So are there any further questions at this point regarding the use of the analysis or complex exponential form of the Fourier series here? Please ask them now. So magnitude versus frequency graphs, basically, it just amplitude versus frequency graph. Sorry, it's basically just knowing what are the frequencies of the individual sinusoids and what are their amplitudes. So for the simple one here, where we just only have one sinusoid, we know that the maximum amplitude will be at 1, and we can calculate the frequency here, knowing what's going to be our periodic time. And for this particular case, we know that the frequency of the graph will be 0.15 Hz, and the amplitude here will just be at 1. But when we have, let's say, a multiple of that same frequency with respect to our sinusoid, with the same amplitude here, we basically have, when we represent it, we still have an amplitude here of 1, but we now just have a different frequency. And in this case, it was 3 times the original frequency, so 3 by 0.15 will give us 0.45 Hz. When we add individual sinusoid signals here with different frequencies, so we had cos of omega t and then cos of 3 omega t here. In the time domain, the signals mix because we basically add in instantaneous values. But when we move to amplitude versus frequency, it's just basically going to be a representation of the individual frequency components here with their respective amplitudes. So the amplitude here of cosine omega t was 1, and the amplitude of cosine 3 omega t was also 1. But the frequency here was at omega, and we basically saw that was 0.15 Hz. And the frequency here was at 0.45 Hz. So we just draw each one of these signals tonally in that particular plot. So we draw our cosine omega t representation here. And then because of the addition, we also draw our cosine 3 omega t, a representation here as of so. So this representation only exists for when you add sinusoid signals together. It's basically the addition of each one of those frequency components, and you just draw each one of those frequency components here respectively, independent of each other on the graph. But this particular plot. So let's say, I'm just going to give you another example of this plot could change a little bit. Let's say we had cosine omega t plus 0.8 cosine of 3 omega t. What this plot will change now is that we have 0.15s and 0.45 here. But our first cosine omega t will have a magnitude of 1, and at cosine 3 omega t, this will just be a magnitude of 0.8, but they're basically going to be at the same individual frequency component values. Alright, nice. Alright, so we're basically out of time at this point, so if there are any further questions, please ask them down in the comments below, or feel free to email me and I'll answer them accordingly for you guys. Remember, tomorrow's lecture will be focusing on the second part of our Fourier series, which will be the trigonometric form and how do we solve for the A0, AK, and BK coefficients in particular. And the solutions for those and the method for those are a little more complex than the analysis form that we saw here today. But it tends to get a little bit easy when you actually start practicing and you know how to watch for certain properties in solving for those particular components. So until tomorrow, take care, be safe, and I'll see you guys soon. Later.